Hello, everyone. Thanks for joining us. My name is Michael. I'll be your host for today. I am a cloud solutions architect from MassDriver. MassDriver is a customizable developer platform that integrates with Terraform, OpenTofu, Ansible, and more, enabling teams to unlock self-service and reduce DevOps requests. During the video, members from my team will be in the chat answering any and all questions. Next week, we're going to be kicking off a 10-week Open Tofu hands-on workshop. If you're interested, hang on until after the video, and my CEO, Corey O'Daniel, will join and share the details. So today, we're going to be talking about how to get started with Docker, the best practices for containerizing web apps using Docker. We're going to be covering some basics of Docker and the Docker file, the essential Docker file instructions, and then we'll finish with a discussion of Docker file best practices. And then towards the end, we're going to be doing a demo on deploying a Dockerize application onto AWS using an EKS cluster and then MassDriver as well. Without further ado, let's get started. So what is Docker? Docker is a tool that simplifies the deployment of applications by packaging them into containers, aka isolated environments, that run on the host operating system. Its main advantage is enabling users to consistently package and run applications across different environments, ensuring portability and reproducibility across various platforms. Now, what is a Docker file? A Docker file is a text document that outlines all the commands needed to build a container image, acting as a script with step-by-step instructions for creating the container environment. Let's check out this example. Starting at the top, we have a comment marked out by the pound sign. This specific comment is a Docker file parser directive. This specifies the Docker file syntax version, which in this case is version 1. This ensures the file remains compatible with the latest Docker features, and Docker treats lines starting with a pound sign as comments unless they are valid parser directives. Although they're optional, parser directives influence how the Docker file is processed. Next, lines 2 through 8, they contain Docker file instructions. Each instruction creates a new image layer and tells Docker what action to take. For instance, the from instruction specifies the base image, in this case, Golang 1.20-alpine. While instructions are not case sensitive, it is best practice to write them in uppercase for clarity. Docker executes the instructions in order, starting with the mandatory from instruction. Each instruction contributes to building the final image layer by layer. Let's briefly talk about layers in Docker. This image here illustrates how a Docker file is transformed into a container image made up of layers. Each instruction in the Docker file corresponds to a layer in the final image. The order of these instructions is important because Docker builds the image step by step, creating a new layer for each command. These layers are cached, meaning if nothing changes in the earlier steps, Docker can reuse existing layers, making builds faster. Understanding this layering system helps you optimize your Docker file for more efficient builds. We'll dive deeper into how you can take advantage of this in a little bit. Let's talk about the Docker CLI next. The Docker CLI is a powerful tool for interacting with the Docker daemon named Dockerd. And this daemon is responsible for managing containers. Through the CLI, you can issue commands to control every aspect of containerization, from pulling images to running, stopping, and managing containers. While we won't go through every command in detail, this table gives you an overview of some of the most commonly used commands. These form the core operations you'll need when working with Docker. We'll see many of these in action during the demo we're about to do in the terminal. Let's go ahead and swap over to our terminal. Now, the first thing that I want to do is run Docker version to see which version we're running on. So I can run Docker version. And as you can see, we're running on version 26.1. So now what I want to do is I want to pull the official Mongo image from Docker Hub. It'll just take a few seconds here. Pull Mongo. I don't think there have been any changes since the last time I pulled it. And nope, so that went really quickly. That's great. So now I can run Docker run -d. -d runs the container in the background for me. -p to set the port, 8080-80. -it is for interactive, and then Mongo. So now we have this container running, and we have it running in the background. But how do we see it? We can run Docker PS. Docker PS shows us all of our containers that are up and running. And as we can see in the top, we have our Mongo image there. So now I want to exec into the container, kind of like we do with a virtual machine. And I can do that with the exec command and the container ID. So I'm just going to copy the container ID here, paste it, and then add bash at the end. And this sets up a bash shell for us for that container. Now I can run mongo d -- version to see what version of Mongo I'm on, and I'm on Mongo version 7. Awesome. This is all I need. I'll go ahead and exit for now. I can stop the container using Docker stop and the same container ID as before. And then to verify that container has been stopped, I can run Docker PS again. And we don't see Mongo up there. So we don't have that container running. Excellent. So now what I want to do is I want to go ahead and make a new directory. We'll call this hello, and then we'll cd into hello. We're going to create a new Docker file here. And let me go ahead and paste one in from here. And essentially what we're doing is we're setting a Docker file parser directive. We're setting the from image, the Golang image, and the tag. We're setting a working directory. We're copying some files. We're running a command, and then we're setting an entry point for the container. And I'll go over these all in detail here in a little bit. Now, let me go ahead and make a new Go function, hello world.go. And then I'll go ahead and paste this in as well. Simple Golang hello world function. So if I run go run hello world, we have hello world, go build hello world, and then execute hello world. We have hello world. Excellent. Okay, so the next thing that I want to do is run docker build -t hello and then dot. So the docker build command will build the Docker image for me. -t allows me to set a name or a tag. And then the dot is the build directory. So essentially I'm saying this is where the Docker file lives. And that's going to run. Okay, cool, that finished up. Okay, so now that that image is built, I can run docker run hello. And we have hello world. Excellent. So we just made an app, tested it, built the image, and we tested it, made sure it was running locally. We can actually now push it up into Docker Hub. So I can run docker build -t. We'll just rebuild it by prefixing it with the public repo for my Docker Hub. And then we can run docker push, same Docker repo name, and then the image name /hello, and that's going to push it into Docker Hub for me. Okay, perfect. Let's go ahead and move on and dive a bit deeper into the Dockerfile instructions to understand what each line actually meant in that Docker file. So choosing the base image. The from instruction starts a new build stage and sets the base image for your container. You can choose any valid image, many of which are available on Docker Hub. In this example, the Docker file pulls the official Golang image, specifically the 1.20-Alpine version. Now I say version, but that's actually the tag of the Docker image. The tag is optional. However, if you omit it, the Docker file will automatically default to the latest version, and it may not be the version that you want. Executing commands during an image build. The run instruction executes a command in a new layer on top of the current image, then commits the result. Each run command creates a new layer, and the resulting image is used as the base for the next step in the Docker file. For example, the line run pip install AWS CLI, that instruction installs the AWS CLI in a new layer, which becomes part of the image before moving on to subsequent steps, such as the CMD instruction. The copy instruction copies files and directories from a source path to a destination path within the container. The add instruction works similarly, but has additional features, such as the ability to copy from remote URLs and automatically extract tar files into the container. Let's break down the example in the image. Line 1, copy dot dot, actually copies everything in the source local directory into the root directory of the container. Line 3 creates a new app directory in the container and then copies the test.txt file from the local source directory into the new app directory. Line 5, add, and then an argument equals true, and then a GitHub URL. This line creates a new app directory in the container and copies the remote repository from GitHub into that container. The argument that we have set, this ensures that the .git directory is also included in that copy. If you don't want the .git directory, you can omit the argument or set it to false. Setting environment variables. The env instruction also sets environment variables in a key value pair format. So in this example, I'm setting the environment variable of my dog to Roger. Environment variables set with env will persist when the container is run from the image. If you only need a variable during the build process and don't want it to persist, you can use the arg instruction instead. Additionally, you can override an env variable at runtime using docker run-e. So for example, if I want to change my dog from Roger to Spot, I can run docker run-e my dog equals Spot. Defining the working directory. So the workdir instruction sets the working directory for any run, CMD, entry point, copy, and add instruction that follow it in the Docker file. If the specified directory doesn't exist, Docker will create it automatically. By default, if no working directory is defined, the working directory is then set to the root directory in the container unless it is otherwise specified in the base image. To avoid potential issues when working with unknown or unintended directories, it's best practice to explicitly define the working directory in your Docker file. Specifying exposed ports. The expose instruction informs Docker that the container will listen on specified network ports at runtime. Both TCP and UDP are supported, with TCP being the default protocol. However, expose doesn't actually make the port accessible externally. It serves as a documentation to signal which ports should be opened. To make ports accessible, you need to explicitly publish it using the -p flag with the docker run command. Running commands or scripts at container startup using the CMD and entry point. So both CMD and entry point have two forms. There's the shell form and the exec form. The exec form is generally preferred because it directly runs the command without invoking a shell. It is written as a JSON array, so you need to use double quotes around the words within the square brackets. In contrast, the shell form runs the command through a shell, which means it allows for shell features like environment variable substitution and string manipulation. So for example, in the exec form for echo and then $home, this will not perform variable substitution for $home. If you want shell processing, like variable expansion, you can either use the shell form or explicitly invoke the shell as seen in line 3 of the example. When using the exec form and invoking a shell directly, or when using the shell form, it's the shell that handles environment variable expansion, not Docker. Let's break down the differences between these two instructions. The CMD provides defaults for executing a container. It can specify both parameters and an executable. If you don't specify an executable with CMD, then you must set one with entry point instead. Unlike run, which executes commands at build time and commits the result to the image, CMD doesn't run at build time. Instead, it defines the default command for when the container starts. Additionally, CMD can be overridden by passing different commands when you run the container using Docker run. Entry point, on the other hand, is similar to CMD, but has some key differences. It always requires an executable and cannot be overridden by arguments passed to Docker run. The purpose of entry point is to define a command that will always execute when the container starts, regardless of any additional arguments. The breakdown in the slide here highlights these differences and shows both the preferred exec form and shell form for both instructions. Now let's check out an example of a Docker file that, when run, will ping localhost in our terminal. We're back in our terminal here. Let's go ahead and make a new directory. We'll call this ping, and then we'll create a new Docker file, and I'll just paste one in here. So we're setting an image of Debian with the Wheezy tag. We're setting an entry point of /bin/ping and a command of localhost. So now if I run docker build-t ping dot, this will build our Docker image for us. And then I can run docker run ping-it ping. And as you can see, we're pinging localhost, so that's great. Now I can see how the Docker file, the Docker image, interacts with an argument. So I can run docker run-it ping and then add massdriver.cloud. And as we can see, we're pinging massdriver.cloud. Great. So let's go ahead and change up our Docker file here. We're going to remove entry point, and instead we're going to add /bin/ping in like this. So we're essentially changing the structure of our Docker file, that instead of entry point and CMD, we're just using CMD for both the executable and the parameter there. So let's rebuild docker build-t ping dot, and then docker run-it ping, ping the local host again. Excellent. So what happens if I try to run-it ping and then massdriver.cloud? Let's see what happens when I run this with this structure. I'm actually getting an error now that's saying massdriver.cloud is not an executable. So this is kind of what I expected with changing the structure of my Docker file. But let me show you this. If I run docker run-it ping and instead echo hello world, sure, we'll leave that in. Actually, I didn't like that. Hello world. Yeah, hello world. There we go. Hello world. So now we can see that we're actually passing in a parameter into the Docker image, and it's executing that instead for us. So as we can see, the structure of how we build our Docker files impacts what our containers essentially do during startup. Okay, let's go ahead and move on now that we kind of got that instruction demo out of the way. So let's talk about some Dockerfile best practices. We're going to wrap up the theory of this video by discussing the best practices for Docker files. We're going to be specifically focusing on layer caching, the .docker ignore file, and multi-stage builds. We'll start with layer caching and how to optimize build times. As we've covered earlier, Docker files are built in layers, and each instruction adds a new layer to the image. When you build a Docker image, Docker tries to reuse layers from previous builds. This is known as cache layers. If a layer hasn't changed since the last build, Docker will skip rebuilding it, significantly speeding up the build process. In the image here, you can see how each instruction in the Docker file results in a new layer. By carefully ordering your Dockerfile instructions, especially the ones that change frequently, you can take full advantage of this caching mechanism to reduce build times. Layer caching. As shown in this image, if a layer of the image remains unchanged, then Docker will reuse that image from the build cache, which is indicated by the green check mark. However, if a layer has not changed, if a layer has changed, that layer and all subsequent layers marked with the red X's will need to be rebuilt. This is crucial because in practice, you'll often find yourself rebuilding the same Docker image, whether it's for a new release or during local testing. And since building images is a frequent task, caching helps speed up the process significantly by reusing unchanged layers. Understanding how to optimize your Docker file to take advantage of layer caching can save a lot of time in the development and deployment process. To optimize your Docker file and make your builds faster, here are a few key approaches. So number one, order your layers strategically. Place less frequently changing instructions, like the from instruction and the dependency installs at the top. This allows Docker to reuse those cache layers, even if subsequent layers change. Number two, keep layers small. Limit each run, copy, and add instruction to only what is necessary to reduce the size of individual layers and improve caching. Minimize the number of layers as number three, and this you can combine related commands into a single instruction whenever possible to reduce the number of overall layers. The attached image highlights how optimizing the order of your layers can increase caching efficiency and improving build speed. Setting your instructions in a logical order is key to optimizing build times because any change in a layer will invalidate all of the following layers, requiring all of them to be rebuilt. To improve efficiency, place the steps that change frequently closer to the end of your Docker file. Let's compare the two examples in the slide. In the top left, we have the inefficient Docker file. This Docker file copies all files at once, which means that every time a file changes, even if it's unrelated to dependencies, Docker has to reinstall all dependencies from scratch, which is an inefficient use of layer caching. The Docker file on the bottom is optimized. Here, we split the copy command. First, copying only the package.json and yarn.lock files, and then installing the dependencies before copying the project files. This way, the dependencies layer only needs to be rebuilt if the package files change. When project files change, the dependency layers are reused, significantly speeding up the build process. By reordering the instructions to install dependencies earlier, we avoid redundant builds and make the most of our Docker layer caching. Another way to speed up your image builds is to keep your layers as small as possible. This means excluding unnecessary files, installing only the required packages, and using the run cache efficiently. Let's start with excluding unnecessary files. In line 1, the top example, we have the copy dot and then slash source command. What this does is it copies everything into the build context, including logs, temp files, and other unnecessary data. Line 3, this copy command is more selective, copying only the essential source files, asset directories, and the make file, which helps minimize what gets included in the image, reducing the build size and the time. Now let's talk about caching with the run instruction. The run instruction in the bottom example uses a specialized cache. This cache stores the contents of the target directory between builds. This means that when rebuilding, Docker can reuse the cache packages and only fetch updates, which speeds up the installation process. By carefully managing the files you copy and leveraging caching, you significantly improve your Docker image build times. Another effective way is to exclude unnecessary files from your image using the .docker ignore file. Before the Docker CLI sends the build context to the Docker daemon, it looks for this .docker ignore file in the same directory as your Docker file. If it exists, the CLI modifies the build context to exclude the files and directories that match the patterns specified in the .docker ignore file. This is useful for preventing large or sensitive files from being sent to the daemon or included in your image via the copy or add instructions. Let's quickly break down an example of the .docker ignore file. In line 1, we have a comment. Comments are denoted by the pound sign and they're ignored. Pretty simple. Lines 2 through 3, the asterisk is a wildcard that matches all files or directories. In these lines, it excludes files or directories named temp at a different directory level. The line 4 question mark, the question mark is another wildcard character that matches any single character. So this pattern would match files like temp1, temp2, etc. And then in line 5, we have the exclamation point, which negates the pattern, making an exception to include any files that match temp asterisk, even if they were excluded by earlier patterns. Using .docker ignore, we can effectively reduce the build context size and ensure you only include the necessary files in your images. And then finally, let's explore multi-stage builds and their effectiveness. In the Docker file, each build begins from the from instruction. There are two main benefits to using multi-stage builds. There are the parallel build steps for number one. Parallel build steps essentially allow you to run certain build steps independently, making your overall build process faster and more efficient. And then the second benefit is smaller final image. So multi-stage builds help you create a final image with a smaller footprint, containing only the necessary components to run your container. Let's walk through how we can reduce the image size by modifying our earlier Docker file. So in this example here, in the Docker file for the slide, we've introduced a second stage using the minimal scratch image as the base. In the second stage, which is lines 8 through 13, we copy over only the binaries built from the first stage, which is lines 1 through 7. This way, the final image contains only the essential binaries, with everything else from the build process excluded. By using this multi-stage approach, we significantly reduce the size of the final image compared to what we would have had with a single stage build. Now that we've reduced the image footprint, we can further improve build speeds by leveraging parallelism. In the previous example, we built the binaries, which were the client and the server, one at a time. However, there's no dependency between the two, meaning there's no need to wait for the client to finish before building the server or vice versa. In this updated Docker file here, we've split the binary building steps into separate stages, lines 9 through 14. By doing this, Docker can build the client and the server binaries simultaneously in parallel. In the final stage, lines 16 through 19, we copy the binaries from their respective build stages into the minimal scratch image. By splitting the builds into multiple stages and reusing the base image, Docker can optimize and run the stages in parallel, significantly improving build times. This approach ensures that both binaries are built at the same time, speeding up the entire process. Well, we've optimized the build by making the final stage smaller and introducing parallelism. The current image still contains both the client and the server binaries. Ideally, we want to separate these into their own images. In the example on the left, we've modified the Docker file to create a separate client and server image. We've done this by using the dash dash target and dash dash tag arguments during the build process. And using them, we can now specify which part of the multi-stage build we want to target. In the output shown on the right, you can see that the client and the server binaries are now built as separate Docker images, each with its own tag, reducing the size and keeping the images more modular and efficient. Okay, so that concludes the presentation getting started with Docker, introduction to the Docker file instructions, best practices. We're now going to go on to the demo portion, and I'm going to deploy a Dockerized application for an AWS EKS cluster using MassDriver. Let's go ahead and get started. So we'll go back to our terminal here, and we're going to cd into our rock, paper, scissors directory, MassDriver. So if we look in this directory, we have an RPS file. I can just bat it real quick. This is just a simple rock, paper, scissors game in Python. If I run py rps.py, oops, we're not in the virtual environment. That's okay. I'm not meaning to run this locally. Essentially, what I want to do is I have this Docker file here. I want to build this Docker image, and then I'm going to push it into my public Docker Hub repo. So we can take a look at the Docker file here. All we're doing is we're installing the Python 3.10 image. We're copying some files into the app directory. We're installing our dependencies, exposing a port, and then we're executing the application. So let's go ahead and run docker build -t, so of course /rps, and then dot. And this is going to build out our image for us. And then we can run docker push mc/rps. So this works for us. This works for essentially non-Mac users. I'm running a Mac. The way that Mac works and running Mac-built Docker images on Linux or Windows architectures, I actually have to run a little bit of a different command here to get this to work, since my EKS cluster is going to be running Linux. So I can still use Docker, but instead I'm going to use docker build x build --platform Linux/AMD. So this is going to specify the platform to build for -t absolute core/rps --push. So it'll push it up to Docker for me, and then dot. And this is going to build that for me. There we go. I had an error there before that I had to update Docker to resolve. So I updated Docker and that error went away. So great. So I went ahead and I built and I pushed my Docker image specifying the architecture of AMD64 to my Docker Hub. So now the next thing that I want to do is make a new application within MassDriver, making a new application bundle template. So to do that, I'm going to run mass bundle new. And then I'm going to go ahead and start that over, mass bundle new. There we go. And then we're just going to call this RPS for rock, paper, scissors. My rock, paper, scissors game And then we're going to select a template here. Because I'm running on AWS EKS, I'm going to select Kubernetes deployment. I don't need any dependencies here, but if I needed a dependency such as AWS Event Bridge or SQS, S3 bucket, all of these dependencies are here for me so that I can customize my application. But since I don't any, I'm just going to hit enter, and then we're going to output into mouse driver. Now, if I cd into mouse driver, we can see we have some bundle files here. I'm just going to run mass bundle publish. And that's going to publish the bundle into mouse driver for me. Okay, so let's go ahead and switch into mouse driver. And as you can see here, I already provisioned a VPC and an EKS cluster for me for the demo. We'll do a quick refresh here, and then we're just going to search for RPS. And as you can see, we have my RPS bundle here. So we'll call this rock, paper, scissors. We'll add it to the canvas. And then it's going to automatically do the connection for me. So now we have my rock, paper, scissors application already connected to EKS, but it's not yet deployed. So what I need to do is go to the configure tab. For the repository, I'm going to type in my Docker Hub public repo, and then the image that I'm using, which is RPS. Set the image tag to latest. We're going to allocate some resources. So I only need like half a core, 100 megs of memory. The port is 5,000. That's what we set in the Docker file. And then I'm going to enable public internet access and set DNS right here. And then we'll click deploy. So what this is going to do is this is going to run the deployment of my application into EKS, specifying the Docker image that we built and pushed in the previous step there. So this will just take a couple minutes or so. I'm going to go ahead and come back when this is. No, spoke too soon. It already finished. Sweet. Okay, so that deployed successfully. So now if I switch into a new tab, and we're going to wait on DNS propagation here. So just take a second. Oh, there it goes. Just had to wait for DNS to propagate. Okay, sweet. So yeah, that's the URL. So now I can go ahead and play my game. Rock, paper, scissors. Awesome. This is exactly what I want. All right. So this concludes the Docker Hub, or sorry, the Docker and Dockerfile best practices, getting started, the video of how it works, and then deploying my application onto AWS EKS using my Docker image with Master Driver helping me out. So thanks so much for joining us. My CEO, Corey O'Daniel, is going to step in to talk about the Open Tofu hands-on workshop. So thanks again for joining us, and take it away, Corey.
Hey, everybody. Before we wrap up today, I wanted to share some exciting news. As one of the companies behind Open Tofu, the open source fork of HashiCorp Terraform, we're committed to supporting the infrastructure as code community in meaningful ways. We did a 4-hour live stream recently on getting started with Open Tofu, and I got a lot of feedback. People were really interested in the session, but it was just way too much packed into 4 hours. So next Wednesday, we're launching a free 10-week hands-on workshop series focused on different aspects of Open Tofu. So they're going to be bite-sized sessions, so essentially 1 hour a week. The idea is we want to get people involved, working in infrastructure as code, being able to work on a project that spans 10 weeks that you can actually see grow. But we didn't want people to feel like they had to spend like an entire day in the session. I've met a ton of teams struggling to adopt IAC effectively over the past couple of months. And our goal is to bridge that gap by offering practical real-world training that helps you confidently roll out infrastructure as code using Open Tofu, the fastest growing IAC tool on the market today. So we're opening up the workshop. It's going to be 50 seats for the first one. You all are the first people that we're telling about this. I'm about to announce it in our community Slack channel as well. Let me throw the banner up here with the URL in it. I'll drop the URL in the in the chat as well. 1 second. Let me just throw it over here. There we go. So what you can expect from the workshop, we're going to do hands-on coding sessions that build on each other each week. So there'll be a GitHub repo with each week in there. And we'll start very basic and kind of build up an interesting 3-tiered architecture. You'll get guidance from the team. So we're directly involved in OpenTofu's development. We'll have a Slack channel. So in between sessions, if you've got questions or you're stuck, you'll be able to ask somebody like how to move on to the next step. There'll be an interactive learning environment. So we want to be able to have these webinars or workshops to be a bit more interactive. So not just us kind of showing how to do things, but actually show it, talk about it, and then kind of experiment with it in real time. So if you're ready to take your infrastructure as code skills to the next level, we'd love for you to join us. Like I said, the seats are limited. We're only going to do about 50. For this first one, we're going to do another workshop, I think probably in late Q4. But feel free to share the link with coworkers, colleagues, friends that you know are interested in learning infrastructure as code. And that's it. Thanks for your Wednesday morning or afternoon or evening, depending on where you are. I'll just keep the session open, the stream open for a little bit longer in case anybody wants to grab that URL. But thanks so much for the time.